Hi, welcome to another edition of Linear Algebra. Today we are going to continue our conversation about the inverse of a matrix and in particular get into the important topic of elementary row matrices. So you remember we said our long-term plan is to redo all the mathematics we know but do it for matrices. And we have learned about the addition and subtraction in transpose. They were all elementary, nothing big deal about any of them, until we came to multiplication and division, where things became quite a bit more involved. So let's go ahead and remind ourselves about that issue of matrix inverse as a starting practice. And then the next topic would be, this is such a complicated operation. Can we break it down to small steps so that we can actually understand those steps? So let's go ahead. So inverse of a matrix and elementary matrices. Here I have chosen a matrix from one of your homework problems to find the inverse of. Another demonstration of Gauss-Jordan method. We said we go ahead and try to eliminate items below the main diagonal and above the main diagonal and create an identity matrix out of M. Meanwhile, do the same thing to identity, and that is going to give us the inverse. So the procedure was this: we take the matrix M and augment it with identity. So if this is 4 by 4, I'm going to make a 4 by 8 here. And then we're going to apply Gauss-Jordan steps to this all the way until this left side becomes identity. And we said whatever survives on the right hand side is going to be the inverse. Okay. Typically quite a few steps are involved, and we said we are going to use that software. We have the web app for helping us do this thing quickly and not get bogged down with arithmetic. So let's go ahead and practice that issue one more time and then come back and say, well, this process was so lengthy. Can we break it down to small steps so that we can understand the individual steps? So let's go ahead to our favorite software of this semester. We want to edit this thing, and we said that's 4 by 4, so I need to make 4 by 8 here because I want to make room for identity. So here the matrix entries I had was 0 at the first, and then it was -1 and then 1. So here I'm just entering, just to remind you, we're just entering this matrix, and next to that we are going to put identity. So identity is going to be 4 by 4. It's going to occupy a few more of those squares. So this was 0. Next I want to put identity, so here will be a 1. Oh, sorry. This will be a 1, and these will be 0. In the second row we had 2, just 2, 1, 0. So you tab through, and then on the right side we are making identity. So identity, there's going to be a 1 here and everybody else 0. Then we come to the third row. We had a 1, then -1, then a 3, and then a 0, and here we get a 1 in this location. Then we go to the fourth row with a 0, 1, 1, -1, and then here I have 1 here. Okay, so we go ahead, double check, make sure we have entered the correct entries here. It's always a good idea to double check everything, otherwise we have to do everything all over again. So on the right hand side is easy to check, it's just ones on the diagonal. Okay, once we are done with this thing, click resume, and we get ready for our operations. So of course I want to have a pivot of 1 here is 0, so I better exchange with somebody underneath. It's your choice if you want to exchange with row 2 or row 3, is all the same. So I go this and click on that, and you saw what happened. 2 came up here. Then we said we like our pivots to be 1. To do that, you divide by 2. The way you divide by an element is click on an element and the row number. Then this is our favorite pivot of 1. We use it to eliminate items underneath. Click on the pivot, click on the target. The operation that was done is recorded down here, so we know what elementary row operation was done here. So here I have a -1. I like to have a 1. It's just conceptually easier to think about it like that. You divide by that. Okay, so click on the pivot, click on the row number, and it just makes it into 1. And then I use this as a pivot, and this is my target. You saw it made it into 0. That's the operation we carried out. This, use it there to eliminate this one. Again, we like this to be 1, so I divide the row by that. The way I divide by row, by the pivot number, is to click on the pivot and then click on the row number. Okay, you saw it made it into 1. Then use this one to cancel 2. So click on this, click on the target. It's all done. Again, we want to have a 1 here. I click on that, click on the row number. That multiplied it by 3. That's what you see the operation carried out here. Now use this one to eliminate that entry. Use this one to eliminate that entry, and we are done. By the way, if we had reached a situation where the entire row was 0, that's a red flag that the matrix does not have an inverse. We had talked about this previously. If the pivot and everything underneath it is 0, the process breaks down. We cannot go any further. Okay, use this one to eliminate that. Use this one to eliminate that. What happened? On the left hand side, we have the identity. What is on the right hand side? This is going to be our inverse. So relatively painless compared to actually doing it by hand. As the size of the matrix grows, we said the number of operations you go through increases with the cube of the size of the matrix. So like 100 by 100 compared to 10 by 10 costs 1,000 times more. Okay, so this is our inverse. We just report this 4 by 4 as the inverse. Again, if any of the pivots became 0 and underneath it was all 0, so you couldn't use the exchange operation, that's a sign that the process is broken and the inverse does not exist, and that's where the problem stops. So what we have done here is that after that operation, we found that the Fm inverse, the matrix on the right hand side, it was 11 minus 2, 5 minus 4, 4, 1 minus 2, 2, 5, 1 minus, is that right? Minus 2, 2 again, 9, 2 minus 4, 3. Let me double check, make sure I copied it correctly. Well, there could be accidentally same, it's fine. Well, yes, these are, looks like, let me double check one more time. 4, 1 minus 2, 2, 5, 1 minus 2, 2, 9, 2 minus 4, 3. Okay, it looks like we are on the right track. So this is M inverse. Now what does that mean? Again, what that means is that if I take a M and M inverse, or M inverse and M, and multiply it, either way I get the identity that is almost magical. Like take this row and then multiply by that column, you're going to get 1. Take this row, multiply by that column, you get 0, 0, 0, and so on. Okay, we carry these things out and we kind of get overwhelmed. There's a huge number of things going on, and it's like watching a huge factory. On one end some raw material come in, and on the other end some car comes out, and God knows what's going on in between these two steps. So we try to understand matrices a bit better than just doing the arithmetic. So the trick lies in the following. The trick is these things that we were doing, the elementary row operations, they are really the clue as to what is really going on. There's a large number of these little steps going on, and if we understand these steps, we understand the matrix inverses, multiplication, and so on. So a deep way of understanding advanced operation with matrices relies on understanding these operations. So we are going to go take a look at them and see in which way is that representing a matrix multiplication or a division, and that is going to give us some insight. It's a little bit like in chemistry. You have this complicated material, and then you break it down to its atoms and molecules and such. You understand the structure better that way. In ordinary mathematics, a long time ago, for example, you learn about multiplication and all the numbers, and then you started learning about prime numbers. You started thinking that every number can be broken down to smaller ones, and those smaller ones you are calling them prime numbers. Like for example, you have 21, you break it to 3 times 7, and you call these things prime numbers because they cannot be broken down any further. In somewhat of a similar manner, we take our matrices and then we break them down to smallest pieces. So it's kind of like an atomic theory of matrices, if you wish. That's what we are going to try to do. So again, everything revolves around these operations. Let's just go ahead and quickly review what that operation meant. So we are going to take a look at elementary row operations. Which are intimately tied to so-called elementary matrices, and they kind of explain how things go when the matrices are multiplied or divided and such. Okay, what kind of elementary row operations did we have? The most important of it was to take a row, multiply it by some number, and then add it to some other row. Okay, row I, row J, these are just two different rows, and what I'm doing there is multiplying one of them by some number and adding to another one. Let's take a specific example so that we are not talking in too much generality, but then also I don't want to put specific numbers. That's going to create a distraction. So what I'm going to do here is just I'm going to take a 3 by 3 matrix. It's big enough: A, B, C, D, E, F, G, H, I. So these 9 numbers is just some numbers, and let's pick a specific number for M so that it's also clear to us what's happening. So I take this matrix and I do certain operation on it. Say 5 times row 1 plus row 3. What comes out? So this is an elementary row operation. This is an example of elementary row operation. The most important of the operations is actually that one. Multiply by row, add to another one that was creating zeros for us. So 5 times row 1. So I take 5 times each of these things, and then I have to add it to the third row. So first row stays as it is. So we say multiply by 5, but we're doing that in our head. We are not actually changing it. The operation is to take 5 times this, add to the other one. So 5a plus G, and then 5B plus H, and then 5C plus I. So this is the operation we carried out. Now, we said that operation itself can be represented by a matrix multiplication. Here I ask the following question: what matrix here can I use so that when I multiply with this, out comes this one? So A, B, C, D, E, F, exactly what I wrote up there. 5A plus G, 5B plus H, 5C plus I. Okay, so your job is to do the following. Find for me, in this case, 9 numbers, such that when I multiply these numbers by that column, I get A, B, C, and then I take this second row, multiply by these, I get D, E, F, and third row, multiply by these, that's the only place that something is going to change. I get 5A plus G, 5B plus H, and 5C plus I. Now I want you to think about this thing by yourself and take a few minutes perhaps. It's very important you discover this thing by yourself. It's very simple. It's like almost like elementary school stuff, but you have to have practice with matrix multiplication and a bit of a linear algebra maturity to see what is going on here. So again, your task is to find out these numbers such that when I multiply, I get the exact same effect that this operation was doing. So what we are saying is that these type of operations we are doing are exactly kind of matrix operations. So here's my clue to ask everybody to actually do this thing before I write it down. So you stop and then complete this thing. Okay, so did you try? So I take this row, multiply by this column. Is that right? That's what we were doing. Multiplying this row with this column, and out supposed to come A. So I don't want to have any influence of the D or G in this. I just want to have A in and A out. Well, of course, I need to have a 1 here and 0 in these two locations. Did you think about that yourself? That if I have 1, 0, 0, then of course when I multiply by A, B, C, D, E, F, G, H, I, when I multiply this with any of these columns, it just picks the first entry for me and nothing actually changes. It just comes out just like that. Okay, next challenge again. If you miss that, perhaps you try again. What is going to be on my second row? Again, concentrate on the fact that you want to pick the D and E and F. So when this is multiplied by that column, D should be picked up, A and G should be ignored. So what should I do here? So I ignore A and G. Well, ignoring means converting them to 0. So I better have 0, 0 here and a 1 in the middle. So by now we learned the trick. If you don't want to do anything to your entries of this matrix, just multiply by corresponding section of the identity. If you don't want to change anything, just multiply by identity, and out comes D, E, F. Go ahead and verify. If I multiply this with that one, I get the E. With the third one, I get F, and so on. Okay, now comes the litmus test, and this time I want to change something. I want to what big thing that's left here is that what should I have in this location, so that when I multiply by that, A gets multiplied by 5, so I have a 5A, and then G stays in also. So if I want to multiply this thing by 5, well, I better have a 5 here, so I'll have 5A. and then I want to have a G, so I better have 1 there to pick my G. I don't want to pick a D, so I better have a 0 here. So now I get 5a plus G, 5b plus H, and 5c plus I, because when I multiply this thing by any of these columns, the first entry is going to multiply by 5, the last entry is going to tag along, and that's where I get my thing. So if I have this operation, that elementary row operation, I say equivalent to the action of that is the multiplication by this. So these two go hand in hand. So if I have this elementary row operation, ERO, let's call it, I like to make abbreviation, elementary row operations there, then here I have a corresponding elementary matrix that does exactly that job. That one you were thinking about mixing these things yourself. Now we're saying, well, exact same activity can be done with a multiplication. Of course, if I have 7 here, I will have a 7 here. If it's a 10 here, I have a 10 here, and so on. And you have to pay attention to where that number shows up. So you want to do several examples of this thing to see where that multiplier shows up for you. Okay, next issue. Sometimes you want to undo this operation. That is, from here you want to go back to that one. How would you do that? Let's do it in 2 steps. One is, let's describe the elementary row operation. So I want to reverse, I want to undo this. That's essentially a concept of inverse matrix. I want from here, I want to go back to where I was. How would I do that? So let's write this thing. Suppose I write this thing a little bit on the right. So A, B, C, D, E, F. 5a plus G, 5b plus H, 5c plus I. What operation is going to undo all that damage and take me back to where I was at the beginning? Well, of course, I want to multiply the first row by what again? Let me ask you to participate here. Okay? Oh, sorry. Well, we didn't want to lose our numbers. Okay, here's my Q. What do I do here to undo this 5a, 5b, 5c? Well, now I have to subtract, of course. Is that right? I will say multiply the first row by -5, add it to the last row, and your magic is going to happen. Well, we ask the same question in the context of matrix multiplication. If I have A, B, C, D, E, F, 5a plus G, 5b plus H, 5c plus I, what should I multiply this thing with so that I go back to what I had before I change the stuff? Well, of course, I want to get rid of this -5. These two rows are untouched. Untouched means, well, that portion of identity. I want to get rid of I want to get rid of 5a. So if I multiply the first row by -5 and add it to the last row, I get rid of that tag along piece, and I go back to what I was. So again, this is an elementary row operation, and it corresponds to the elementary matrix that goes hand in hand with it. Now we notice something nice and cute. You remember how many steps we went through to get this. You know, we went through a jungle, essentially do stuff, and out comes this matrix. By the end, you kind of lose track of what happened. Uh, everything checks out, but just too much detail there. Here we come and see this matrix, its action is undone with this matrix. This is the inverse of that, and it's a very simple inverse, that off diagonal entry has turned into the negative of itself. So inverse of this type of an operation is simply done by flipping the sign of that off diagonal entry. Let's go ahead and check it, that if I have 1 0 0 0 1 0 5 0 1, and then I consider this other one 1 0 0 0 1 0 minus 5 0 1, my discovery is that these two are inverses of each other. These are inverses. Why is that such a great thing? Because we understand, at least in one case, in one extremely simple case, that's why it's called elementary. What is the inverse without drowning in lots of Gaussian, Gauss-Jordan stuff and so on? It's just right in front of your face. There is just one thing that's being done. So we are not overwhelmed by gazillion things to do to figure out an inverse, whatever off diagonal entry you have. So here we have identity. Then there is one single off diagonal entry that shows you what multiple of what row is to be added to what other row. The inverse of that is obtained by just flipping the sign to negative of whatever it was. Let's just go ahead and verify. Well, these of course, when you multiply it by these columns, not surprisingly, 1 times 1, you just got 1. When you multiply by these, you get zeros. 0 1 0. You multiply by these columns again, it's I laid it for you to double check. That's 0 1 0, so that's not a big surprise. Now comes the following. The kicker is here. 5 0 1 multiplied by 1 0 minus 5. What's that going to be? 5 times 1, 0 times 0, 1 times minus 5, and they cancel each other out. 5 0 1 times that, well, the way the zeros are, this thing is going to destroy that one. I get a 0. In 5 0 1 times the last column, again this is a 0 entry, that's a 5 there. When you multiply them, you get 0, and there you go. You do get the identity. Okay, so that is what we are selling now, that there are these super simple matrices whose inverse is obtained by so-called inspection, meaning you just look at it. You don't go through Gauss-Jordan, you don't go to the software or anything like that. It's just right in front of your face what the inverse is. Okay, well, we had 3 elementary row operations. You remember we had second row operation. For example, let me go show it to you here on this app. So for example, here 1/2 of R1 goes to R1, and that was the multiplication operation. Again, here's another example of it. When you're making the pivot to be 1, that is what you do. Well, that's a kind of very simple operation. The most important operation is what we already did. The other two is also ran type of thing, but let's go try it again. So suppose I have, again, my favorite 3 by 3. Of course, we could do this thing to any size, but then I have to sit down here and write huge number of letters and such. So suppose I have 4R3. Let me write it here. I'm doing operation 4R3. Okay, so what does that mean? Multiply row number 3 by 4. How about the others? Or just leave them alone, so not anything done to them. So this is 4G, 4H, 4I. Okay, that's how we used to talk about this operation. Now we are saying that operation you're doing is really a matrix multiplication. And again, I'm going to ask you the following. If I have, sometimes you have to adjust the size of matrix to get what you want. So again, in this case 3 by 3, and I ask the same question as I did last time. Give me 9 numbers such that when I multiply I get the same thing that this one was doing. So we are duplicating the effect of the so-called elementary row operation by a multiplication. We are saying these are really same thing. Well, again, the first 2 rows are not being touched. Do you remember from last time? What does that mean? So again, you want to pause this thing, tell me what is these 9 numbers, and come back and cross-check what you thought with what I say. So I'm not changing first 2 rows. That is a clue that if I use that portion of the identity, that is gonna leave everybody go through untouched. Essentially, they go through, they are untouched. Now I want G to be quadrupled. What should I put? I don't want any interference from A or D. I'm not picking on those things. I'm just multiplying this thing by 4. So what do I am not picking on A, I'm not picking on D, I'm just taking G and multiplying by 4. So again, what we are learning is that this elementary row operation matches to this elementary matrix. Whatever that is doing, this is doing exact same thing. Very different style though. Previously there was an off diagonal entry that would tell you what multiple of a row you're adding to another row. That was a little bit more complicated. This one, you are multiplying a row by a certain number, and that entry of your identity has to be exact at that number. So for row 3 you are changing stuff on the 3rd entry. Okay, so these are the same, and same question as before. If I want to go back, so if I have if I am here A, B, C, D, E, F, for G, for H, for I, and I want to undo this damage or this modification so that I go back to where I was, A, B, C, D, E, F, G, H, I. So first let's talk about operation. How do you go back? Well, obvious. You take the 3rd row, now divide by 4. Previously you were multiplying by 4. So opposite of multiplication, of course, is just division. Different than this case, where the opposite of addition was subtraction. Here opposite of multiplication is division. So you shouldn't get the 2 of them confused, of course. And if you want to do this thing with matrix style, and so with matrix, how do you do it? Just like what we said, 1, 1, and what number should I put here? I want to multiply these things by 1/4, or just put by 1/4, and of course these are all zeros outcomes. What we want here, our original matrix shows back up. So this elementary row operation matches to this elementary matrix. Each elementary row operation matches to a particular matrix, and each of these matrices correspond to one operation. Only one number from identity changes in all these matrices. Which number is it? It depends what kind of activity you have. Adding a row to another row, this is off diagonal entry. Multiplying, it is just that entry on the diagonal. Okay, what else did we have? Do you remember the 3rd operation we had? So far we talked about this usually called addition operation. Sorry, what is it? So you addition of a row to another row, so this falls under addition. Sometimes it's just called addition operation. This thing is called multiplication operation. Again, we're just adding nicknames to these things. What else was left? You remember the third operation that we had? Sometimes see, when your pivot is 0, you have to do an exchange, just so that we keep everything tidy and pivots become 1 and such. You need to exchange, not a major operation, but that just keeps things under control. So same thing here. Again, for third round, let me explain the exchange operation. Exchange, sometimes you call it swapping or shuffling or whatever. So suppose I have A, B, C, D, E, F, G, H, I. So you take a linear algebra class and you learn the alphabet. So suppose for whatever reason you want to exchange two of these things, whichever you want, this and that, or this and that, or this and that, whatever you want. Suppose I want to exchange row 1 with row 2, which means what? That the row 2 comes the first, D, E, F. First goes to the second, and third stays put. So again, I have an elementary row operation here. Under that, this happens. I ask the same question: is this achievable by a multiplication? If so, I'll be really happy, because everything we talk about then is going to be matrix multiplication. You know, it's like in chemistry, you say, why everything is made out of atoms. That kind of gives you a grand picture of how things are made. Here you're going to say your matrices are made out of elementary matrices. So that's one way of having a view of a very complicated landscape in terms of small little things, like kind of like Lego blocks of all of this. So let me see if you, again, can you come up with this? So the question again is, give me 9 numbers such that when I multiply, it does exactly what this one was doing. So that one was, we were talking as if we were playing cards and we're taking this and shuffling with that. Okay, that's one type of thinking, like almost physical, like take this thing from here, put it over there. But now we're saying, oh, well, can you do the same thing with multiplication? Multiplication is kind of more respectable than if you wish, than shuffling cards and stuff. So what do I need to do? I need to take this, multiply with that, and what is it that I want to pick out? I want to pick the D. Is that right? I want to pick the D. I don't care for A or G. They don't show up here. So what does that tell me in terms of what I need to have in these 3 spots? Remember again, I want to pick on D. Picking on somebody, I need to have a 1 there. Ignoring others, I have a 0 there. So I need a 0, 1, 0. Okay, just try it. If you take this yellow, multiply by this blue, it's going to pick on D. Multiply with this blue, same thing. Pick the second element, pick the second element, and so on. Okay, now I go in the next row and multiply. I want to multiply by this thing, but I want to pick on A, put it here, but I want to ignore D and G. So what does that mean? Did you think that this has to be 1 and 0, 0? Yes. And how about the third one? Well, third one you're not touching. Well, excuse me. Touching means you just copy from the identity and put that thing there. So exchanging row 1, 2, the matrix that does it is like a matrix you get from identity and exchange row 1 and 2. Isn't that neat? So once again, let me explain what happened. First of all, This is the matrix that goes with that. This is our elementary matrix that copies this action. Now, sometimes you want to be done with this thing in a fraction of a second, and we are moving on, as opposed to inventing the wheel all over again every time. How do we quickly come across this answer? If you take the identity and exchange row 1 and 2 of the identity, you get the matrix that when you multiply by your arbitrary matrix, it does exactly the same action. Is that idea general? Well, yes. How can I obtain this? One way is to just go build everything from scratch. What's a quick way? Take the identity, apply this operation to it. So 4 times row 3 on identity, the 1 becomes a 4. That multiplied by any matrix will do whatever that one was doing. Is that really applicable to everywhere? Yes. So for example, here I want to do 5 row 1 plus row 3. So I take the identity, right? Identity equals 1, 1, 1. Add 5 times row 1 to row 3. 5 times row 1 to row 3. A 5 is born in this location. So each of these elementary operations, elementary matrices, are obtained by applying your elementary row operation to identity. So let's write that down because it's important observation. Each elementary matrix is obtained by applying, that's one way of doing it, a quick way of doing it, by applying the corresponding elementary row operation to identity. So that gives you a fast recipe for doing that. How can I make this? Just take the identity. Identity was like this. And then what? To that identity, apply this operation. Exchange row 1 and 2. Well, that's what you are going to get. And the matrix that you get is going to do what you wanted it to do. Okay. Now, what about all of this? What does that mean? Looks like all little trivial things. What does that get me? Let's go back to this. I hope I haven't tired you guys. Let's go back to this. We are doing a bunch of elementary operations. One operation, another operation, another operation, maybe 10, 20 of them. And then at the end comes what? At the end comes this left-hand side becomes identity, right-hand side becomes your inverse. So what? Let's suppose I go to the starting example. I have this matrix, and then to it I applied like 24 operations. I don't write down the detail because we don't want to get bogged down with the detail. So I had the matrix. Then I apply elementary operation, elementary row operation number 1. Then elementary row operation number 2, elementary row operation number 3. Who are these guys? I'm not writing the details of it, but those are exactly what are listed here. Operation 1, operation 2, operation 3, and so on. In one after another, they are being applied. Okay, you have the matrix, then you have elementary operation number 1, number 2, number 3. How many, God knows, depends how complicated, how big the problem is, whatever it is. So I might just write elementary operation, I don't know, number 100 maybe, or whatever it is. At the end of all of these activities, what happens? Well, let's go back here. What happened again? When I apply to my matrix, I get identity. and when I apply to identity I get the inverse. Let's go and explain that and write it to see what happened. So when I apply all of these things, I'm gonna get identity. Okay, and I applied the exact same thing. I start on the right hand side. I had an identity. To all of them I applied same stuff. Whatever it was, say 100 of them, whatever. Out comes what? Let me see if I can pause. See, I haven't lost you. What showed up on the right hand side? What showed up, of course, was M inverse. It's not surprising that M inverse shows up because all of that stuff is what I'm doing here, and that collection times M is supposed to be identity, so that has to be M inverse. Okay, now this looks like a factorization of M inverse. This is a factorization of M inverse. Again, like in Algebra 1 or whatever math you had many years ago, you say 21 and you say, well, 3 times 7. You talked about perhaps prime factorization and such. This is some factorization. It's not quite a prime, but to something that's very elementary. So this matrix factors like this. How about M itself? Now instead of writing 100 of this thing and getting distracted, let me just write 2 of them so that we are not overwhelmed. So elementary row operation number 1, and suppose I got lucky, after 2 operations I was all done, and then I already had identity. Of course, in practice this could go on and on. Well, now if you take the inverse of this thing and I multiply it on both sides, so if I take elementary operation number 2 inverse and multiply with whatever I had here, elementary operation number 2 inverse times identity, this becomes identity, and it's like 1. I don't need to write it. And then by now I have elementary row operation number 1m is equal to elementary row operation number 2 inverse times identity. I can multiply by this thing again, elementary row operation number 1 inverse times elementary row operation inverse m is elementary row operation. You have to be careful where you put it, is of course on the left now. So by now these two become identity, and then m becomes elementary row operation number 1 elementary row operation number 2 times inverse. So you get a factorization for M inverse and a factorization for M. Now for each of these things you might write your matrix E1, E2, E3, and so go as far as it takes, E100. And for M inverse this will be E1 inverse, E2 inverse, and then your identity. So both matrix and its inverse gets broken down to the product of elementary matrices. Each of the elementary matrices are very easy for us to handle. But of course, when you have a whole long list of multiplication of these things, then the complicated things do show up. So again, in this example, the matrix that you have on the right hand side is very hard to envision what that thing is, but when you write it as a product of elementary matrices, that is a little bit easier to digest as to what they are. Okay, so it was a little bit theoretical perhaps, but that was important to see that matrices can be made out of simple things. They're kind of atomic matrices, if you wish. We call them elementary matrices, and we can track a matrix and its conversion to another matrix by these elementary matrices. Okay, There's a lot more to be said here, but we have to make room for other stuff at the end of the semester. So I'm going to be concentrating on eigenvalues and eigenspaces and solution of differential equations, so that we can bring this topic and differential equation together, and what we promised at the beginning of semester, that we are going to talk about movement of compound systems in that example we had with 2 balls and 3 springs. How does that relate to linear algebra? To get there, we need to bypass some theoretical things and do that, and if you have time we'll come back. So until then, good luck and God bless.